Hi, I am Sian Hao, and my project focuses on stratospheric aerosol removal technologies in the event of an abrupt sunlight reduction scenario. An abrupt sunlight reduction scenario, or an ASRS for short, is a sudden and significant reduction in the amount of solar energy reaching the Earth's surface, and can be caused by a large injection of aerosols into the stratosphere, causing the attenuation of sunlight. If left unaddressed, an ASRS can lead to decadal disruptions to the Earth's climate, impacting food production systems all around the world and potentially posing an existential threat to humanity. These are the potential injection events that may lead to an ASRS. Out of these potential causes, nuclear war is the most significant and probable, with a likelihood of occurrence of 1% per annum. It is estimated that the resulting ASRS could cause 2 billion deaths in a nuclear war between India and Pakistan, and 5 billion deaths in one between USA and Russia, thereby highlighting the potential existential risk of a nuclear winter and an ASRS in general. At present, the majority of current interventions fall into two distinct groups: prevention and relief. While these are impactful, there is an aspect of the problem that has received relatively little attention in comparison. That is, reducing the scale or duration of the ASRS so as to mitigate the extent of the disaster and prevent it from posing an existential threat to humanity. My goals for this project are hence to assess the feasibility and efficiency of potential aerosol removal technologies before proposing a design that incorporates the most promising ones. Before diving into the potential technologies, it is imperative that we understand the details of the problem. While the injection events discussed above emit many different types of aerosols, the most concerning ones are sulfate and black carbon aerosols, due to their light scattering and light absorption abilities respectively, as well as their abilities to stay in the stratosphere for extended periods of time. Importantly, the size of these particles falls in the range of 0.1 to 1.0 microns. The natural removal of aerosols in the atmosphere is largely governed by dry and wet deposition processes, which are most effective in the lower troposphere. However, aerosols can take years to settle out of the stratosphere naturally, as there are no surfaces to act as particle collectors in dry deposition, and the low humidity of the stratosphere inhibits cloud and ice formation. With this crucial knowledge, our goal is to facilitate the descent of aerosol particles into the troposphere, where they are more susceptible to wet deposition processes that can further remove them from the atmosphere. We will now look at potential aerosol removal technologies. The 5 technologies that I have prepared include HEPA filtration, short for high efficiency particulate air filtration, electrostatic precipitation, cyclonic separation, chemical scrubbing, and heterogeneous condensation. Each of these have their own set of strengths and limitations, especially in the context of the extremely low temperature and pressure in the atmosphere. Given the advantages and limitations of each of the technologies, I seek to assess their effectiveness using these 6 factors. This is the assessment matrix of the 5 removal technologies. From this matrix, it is clear that HEPA filtration and electrostatic precipitation are the most promising due to their high efficiency over the required size range, their low operational complexity, as well as the availability of the technology required. Therefore, I propose a hybrid multi-stage design implementing HEPA filtration and electrostatic precipitation, as well as a pre-filter that helps to eliminate large particles so as to reduce the maintenance requirements of the HEPA filter. After large particles are eliminated by the pre-filter, particles larger than 0.3 microns are captured by the HEPA filter, while smaller particles pass through to the electrostatic precipitator. This system can be delivered to the stratosphere via high-altitude aircraft such as airships and balloons. Potential enhancements to the design include the utilization of chemical surfactants to enhance agglomeration between aerosol particles in a pre-filtration process. Sensors can also be incorporated into the system to measure the performance of each component, and the data can be used to adjust the operation and maintenance of the system to ensure optimal performance. Additionally, the power requirements of the system could be met by energy sources available in the stratosphere, such as solar energy. Lastly, the mechanism of enhancing heterogeneous condensation may be applied to particles that have descended into the troposphere to facilitate their further removal by wet deposition. In the next phase of my work, I aim to improve the hybrid aerosol removal system by focusing on several key areas. These include comprehensive testing, exploration of advanced materials, optimization of different mechanisms into a cohesive system, enhancing energy efficiency, and the development of monitoring and data analysis tools to continuously assess and improve the system. To conclude, my project has provided an evaluation of various stratospheric aerosol removal technologies, shedding light on potential methods for aerosol removal in the stratosphere and laying the groundwork for future innovations that could enhance our ability to mitigate an ASRS. As we forge ahead, let's remember that our work today contributes to the larger mission of preserving our planet for future generations to come. Thank you.